All right, let's talk about what might just be the single greatest unsolved mystery in all of mathematics. Seriously, it's a problem that has captivated and frankly tormented the brightest minds for over 160 years. It connects the world of prime numbers, which seem totally random, to some kind of deep hidden order.
And yeah, this isn't just for academic bragging rights. The Clay Mathematics Institute has slapped a $1 million price tag on it. If you can solve it, you get the cash, the fame, and a permanent spot in the history books.
And that's not just hype. Proving the Riemann hypothesis wouldn't just solve one problem. It would be like a master key. It would instantly prove hundreds of other ideas that mathematicians have come up with that all start with the phrase, assuming the Riemann hypothesis is true. It's the linchpin holding so much of number theory together.
So how in the world are we going to wrap our heads around something this big? Well, we're going to break it down. We'll go through 5 parts. First, what exactly is this problem? Then, what does it have to do with prime numbers? We'll look at the famous line of zeros, then dig into why it matters so much. And finally, check in on the modern hunt for a proof.
Okay, so let's get right to it. What is this legendary problem? Well, when you boil it all down, it's a very specific question about a very special mathematical function.
And that's it. That's the whole idea. It sounds almost too simple, doesn't it? For this one specific function, all the important inputs that make the output equal 0, what we call the zeros, all line up perfectly. Now, to understand why that simple statement is so incredibly profound, we need to meet the star of our show.
And that star is the Riemann zeta function. The best way to think about it is like a mathematical translator, or a bridge that connects two totally different worlds of numbers.
So on one side of the bridge, you've got this expression. You take every single whole number, 1, 2, 3, 4, on to infinity, and you do a little math with them and add them all up. It's a statement that involves all the whole numbers.
But here's where the magic comes in. Something figured out by the great Leonhard Euler. He realized that this exact same function could also be written in a completely different way, a way that uses only the prime numbers, 2, 3, 5, 7, and so on. This is incredible. It means this one function is a bridge that encodes the secret of how the primes are scattered among all the other numbers.
So along comes Bernhard Riemann. He looks at this amazing function and asks a brand new question. Where does this thing equal 0? He started exploring the function's landscape, and what he found was just baffling.
Now, it turns out the function has some zeros that are, well, they're kind of boring. They're predictable. They happen at all the negative even numbers. We call those the trivial zeros. But there's also an infinite number of other, much more mysterious zeros. These are the non-trivial ones, and these are the ones we're hunting for.
So mathematicians were able to narrow down the search. They proved that all these interesting, non-trivial zeros have to live in a very specific neighborhood. Imagine a map of numbers. All the zeros are confined to this one narrow vertical band called the critical strip. This was a huge step, but the real mystery was still hiding inside. Because here's what Riemann noticed. For every zero he was able to calculate, it didn't just fall randomly somewhere inside that strip. No. Every single one landed on a perfectly straight line running right down the dead center of the strip, a line we now call the critical line.
And that, right there, is the whole thing. The Riemann hypothesis is the simple, beautiful, but incredibly bold claim that every single one of those infinite non-trivial zeros lies precisely on that one-half line. Not just the first 10 or the first billion, but all of them, forever.
And you know, what's so telling is that even Riemann himself, after what he called some fleeting vain attempts, just set the problem aside. He knew he'd stumbled upon something huge, but even he couldn't crack it, and nobody else has for the 160-plus years since. So, okay, let's just assume for a second that it's true. Every zero is perfectly lined up. So what? Why should we care? What does that actually get us?
Well, proving it would be like finding the secret blueprint for prime numbers. It would tell us that their distribution isn't chaotic at all. It follows an unbelievably precise law. Our best guesses for how many primes there are up to a certain number would be as accurate as they could possibly be. It would mean the primes are perfectly balanced, a stunning harmony between randomness and pure order.
And to give you a sense of just how powerful this hypothesis is, check this out. It can lead to some truly mind-bending proofs. For another famous problem, mathematicians managed to solve it by showing it was true, if the hypothesis is true. And then, they also showed it was true if the hypothesis is false. Since it has to be one or the other, boom, problem solved. That's how deep this thing runs.
So where are we today? While a formal logical proof is still out of reach, the hunt has gone high-tech. We're in the era of massive computation.
And the amount of evidence we've piled up is just staggering. I mean, look at this. In 1903, we checked the first 15 zeros. By 1953, the great Alan Turing used an early computer to get past 1,000. Fast forward to today, and we have verified that the first 12 trillion zeros are all exactly where Riemann said they would be. Every last one of them perfectly on the line.
And this is the absolute core of what makes math so challenging. Checking 12 trillion cases is not the same as infinity. Finding a pattern, even one that holds for an unbelievably long time, is not a proof. You need a rock-solid logical argument that shows it has to be true for all of them without exception. And that's why that $1 million prize is still sitting there waiting.
So in the end, we're left with this massive, tantalizing question. The evidence is overwhelming, but a proof is nowhere in sight. Are the primes really just random static? Or do they follow a kind of hidden music, a beautiful and profound law that we just haven't been clever enough to uncover yet? The answer, whenever it comes, will tell us something fundamental about the very structure of our universe.